Um, Hello everyone. I hope you're all doing well and you have all seen all these clips that I have recorded for you. The next one that I want to discuss, which is still got his toes in the GCSE, and then perhaps it's also enormously important in A-level or AS chemistry, is the ability to calculate concentrations of reactions or making standard solutions. You know, when at GCSE you were doing a titration, they would just put solutions in front of you and ask you to get on with it. Now, at A-level, you have to make your own solution of certain concentrations, certain molarities. Make your own standard solutions. And then later on, if this clip is not going to be that long, I'm going to talk about a couple of maybe one or two examples on titration calculations. You know, the simple ones, Mickey Mouse ones, I call them. We'll see how it goes, all right? So, in order to learn anything in chemistry, you have to appreciate its importance. So, why are concentrations important? What are they doing in your syllabus? You see, I always tell my students that if, for example, somebody goes to the hospital and they need to be given an injection, don't you think the amount that is injected and also the concentration of that medication is important? If the concentration is less than it should be, then it may not be effective. If it is too much, then it could cause an overdose. But what about in industry? What about in industrial chemical world? You see, there are certain chemical reactions that require certain concentrations. For example, you're making an ester and you have to add concentrated sulfuric acid as a few drops as catalyst. Well, if it's very dilute, the reaction will not work. You won't be making any esters anytime soon. And there are numerous examples. Yeah, concentrations enormously important. Sometimes it could be to do with health issues, which is very pivotal, and sometimes it's just to do with chemical reactions that we do. If we get the concentration wrong, it simply won't work. Enormously important, therefore. Later on in the course, when we talk about aromatic organic chemistry and how the role of certain, for example, acids that need to be of certain concentrations, and if they are not, the reaction will not work. You know, we'll discuss those in due course. If somebody asks you to make, 10 milliliter of 0.1 molar solution of sodium chloride, let's start nice and simple. Once you get the principle, then you can apply it. Yeah, this is an application subject after all. First of all, let's understand what M means. M stands for molar. Molar. And the unit, of course, is moles per decimetered cube. You can either write it like that, you can put slash, and just write dm to the power 3. So what does it mean? It means you have a solution that if you had 1000 milliliter of it, you would have had 0.1 mole of that solute in it. Now, in order to make this solution, let's go through the procedure very, very quickly, because I don't want this to be as long as the other clips I put up for you. So sodium chloride, the first thing you have to find out is what is the MR of this guy? Well, sodium is, that's 23, and chlorine is 35.5 grams. So it's 58.5 grams, 58.5 grams. So that is 1 mole. Yeah, that's 1 mole. The next step is that if that is 1 mole, then how many grams is 0.1 mole, right? So 58.5 times 0.1, that's 5.85 grams. Agreed? Now, the next thing is that you ought to be thinking is that this amount will make 1000 milliliter. We didn't want 1000. How much do we need to make only 10? So you have to divide that by a further 100. So basically what you need is that 0.00585 grams, yeah? in 10 milliliters. So what do? You have to find yourself a very nice, very accurate balance, right? 85. And then you have to find yourself a 10 milliliter volumetric flask, where it says 10 milliliter, and then there is a line up there. You put your stuff in there, yeah, you put it in there, whatever it is, and then you fill it up with water, with distilled water. You put the lid on, you shake it, there you are, 10 mils. If you have to make 10 milliliter solution of something, you're not going to make half a ton, use 10 mil and then get rid of the rest, do you? Doesn't make sense. You make what you need to make. In chemistry, we don't waste chemicals. Sodium chloride might not be the most expensive of solutes, but what if you have to make, for example, 10 milliliter of silver nitrate solutions, right? Not very cheap. And then there are many other compounds that are even dearer. We make what we need. If you're going to use 10 drops or 10 or 5 milliliter of something, make 10 milliliter and then use 5 milliliter. You would not be wasting that much, would you? So that is that. So this is how you make your standard solutions. So maybe in one of the practical exams or practical that you do, they ask you to make 100 milliliter or 250 milliliter of solution X, whatever that might be. This is normally the procedure. You have to find out what the MR of that is, and then you multiply it by the number of molarity, and then remember that mass is enough to make 1000 milliliter, and then you either have to ratio it down or ratio it up in accordance to how much you actually need. Usually it's 100 mil. And then you have to get a volumetric flask. The only reason you use volumetric flask is to make standard solutions. They are not used for anything else. You don't boil things in them, you don't keep things in them. You just use them to make solutions, standard solutions. Standard solutions that you are going to use in titrations, for example. Okay? So that is that. Now, let's argue let's discuss how would you do the calculation for a titration. Let's use a very, very simple example. So the question might be, let's use a darker color so it becomes more visible on the screen. So let's say that you have used 20 milliliter. I'm using 2 decimal places because remember in titration they could be accurate to 2 decimal places. The last number is either 0 or 5. If when you do the titration, the meniscus is in between the 2 milliliter lines, then it is 0.05. It's a 5, the next number, yeah? If it is sitting dead on it, then it's 0. You see, it is literally 1 drop, yeah? So even though we do it, but they can be extremely accurate. Now let's say you did a few titration, and this is the concurrent titer. You either write milliliter or decimetered cube, it doesn't matter, both of them are exactly the same. So 20 milliliter of say 0.1 molar solution of hydrochloric acid, say neutralizes say 25 milliliter. I'm making it really nice and simple. Again, you learn something, then you apply it to other things as well. 25 milliliter solution of say, I don't know, potassium hydroxide solution. All right? And then the question is, so what is the concentration of this guy? We know everything about the acid. We know the amount that we've used, and we know its concentration as well. Now, what I always tell my students is to approach a 1-to-4 approach. Yeah? And I actually put my name to it as well, the 1-to-4 Dr. Salem approach. But the 1-to-4 approach, number 1 would be you write a balanced chemical equation. Remember what I said, I'm not saying it, I'm just doing it. So write a balanced chemical equation, so you have hydrochloric acid, never mind the state because we want to just do this pretty quick, otherwise it's AQ. Remember what I told you about balancing and neutralization. Well, this guy has got 1 hydroxide and this one's got 1 hydrogen. So it's actually balanced as it is. 1 hydroxide, 1 hydrogen, 1 water. And then you have potassium chloride, KCl. Okay, so the ratio is 1-to-1. The ratio of your acid and your alkali is 1-to-1. So whatever number of moles of acid we've used, we must have used exactly the same number of moles of alkali. So how many moles of acid did we use? We used 20 milliliter, only 20 milliliter, not 1000. 20 milliliter of 0.1 molar solution, right? So that's 0.002 moles of HCl, all right? So if we've used that many moles of HCl, then the step 3 is that by using the ratio, you work out the concentration of the alkali. So the ratio is 1 to 1, isn't it? Therefore, 0.002 moles of potassium hydroxide 2 in this case. Agreed? Well, all right. And then 4, remember, we have to work out the concentration of this guy. Well, you say, if I've got 0.002 moles of potassium hydroxide in 25 milliliter, what was the unit for concentration? Moles per decimeter cube, or moles per every 1000 milliliter. If you've got this many moles in 25 milliliter, how many would you have in 1000? So you have to multiply it by 40, isn't it? Yeah. So this multiplied by 1000 divided by 25. So in essence, you multiply it by 40, and that's 0.08 moles per decimeter cube, which is slightly less than 0.1 acids, right? You use more of it against less of acid, and therefore they neutralize each other. This is just one example. The other examples that you could encounter is that when it comes to the balancing, so for example, if instead of hydrochloric acid I had sulfuric acid, it will affect your ratio, isn't it? So every 1 mole of sulfuric acid would react with 2 moles of potassium hydroxide. So whatever number of moles of acid you found, they wouldn't be the same. In that case, you have to multiply it by 2, right? Etc., etc. Or if it's the other way around. So again, to make this section a little bit shorter, this would be the very last of my kind of GCSE/AS clips. The subsequent ones, we start slightly more serious, more relevant A-level questions. All right. So practice these things and follow the 1 to 4 step. And if the information here, actually, if the penny drops here, it means you can actually apply it to other examples as well. So remember, concentration absolutely matters. If I asked you, whatever number of you sitting there watching this, if I asked you to make a dilute solution of something, literally every single one of you would make in different solutions, and we'll call it dilute. Or if I say, make a concentrated solution of something, again, same scenario. But if I asked you to make a 0.1 molar solution of something, then all of you will be making the same stuff. You understand? Okay. Thank you.